Okay, everyone, we are starting our new unit, Unit 5, which is called Polynomials. Now, this seems like a very complicated word, which I'm not going to describe just yet, but essentially what it is, what we're learning here in this unit, everybody, is the mathematical language, okay? And that is called algebra. So just like when we spell words out and we talk in a specific English language or Spanish language, for example, we're speaking in a language that all humans understand. Well, in math, there's also a language. In math, it is called algebra. Okay? And it deals with equations and expressions and variables and numbers. That is what is in a mathematical language. So we have actually done this a little bit in our last unit when we studied linear equations. So if you remember our linear equations unit, you'll remember that we looked at some real-world applications that used a mathematical language to describe a relationship, right? So for example, when we did the cell phone plans and we knew that there was an initial cost to buying the phone and then a monthly rate that we had to pay on a monthly basis, we didn't use words to describe that. We actually wrote out an equation such as the cost equals, let's say your monthly payment was $75 a month. So 75 times the number of months, or 75x, or you can use any letter there, plus, let's say, the initial cost of our phone, we had to pay $500, right? This is a mathematical language, okay? That is what this is here. We didn't use necessarily words to describe it. If you look on paper, all you see is numbers and variables, okay? Variables meaning letters. So, made up of numbers and variables. That's what algebra is made up of. Okay, and it's a language. So this unit, we are actually studying some of the rules that apply in simplifying this language of math, this algebra. Okay, and when you think of real world examples all around us that use algebra, I think you'd be absolutely shocked. I'm only going to list a few of them now, but there are so many, it's all around us. There are so many real world applications where formulas are used to make our lives better, easier, and whatnot. For example, computer games is a big one. So, not sure if you were aware of this or not, but in a computer game, there's a programmer who's programming in mathematical formulas that help describe real life motion. So when we look at a video game and we see a person, a virtual person there that's moving just like a human being would move, that just doesn't happen by chance. That's a programmer that has modeled certain motion through equations and formulas of human beings, and then programming that into the video game. And so when you look at it in the video game, you're seeing this lifelike motion, right? And we just see the end product, but in behind the scenes, there's hundreds and thousands of formulas that are used every second, everywhere that your character in your video game looks around, and everything, every object that is seen, it's all mathematical formulas that were built into that video game. So that's one major example. Medicine is also another example, of course. If you become a doctor or a nurse, you need to have some knowledge of formulas. If you're giving, let's say, an IV to a patient, for example, and you need to calculate how much to give them, and all of these different things here, all these different types of medicines that a patient might receive, formulas are involved, equations are involved. So this mathematical language is involved in some way, shape, or form. Something as simple as the traffic lights in our city. Um, they're also programmed by human beings with mathematical formulas to time the lights to either hit green at a certain time or hit red at a certain time. Let's say the city has deemed a certain road to be dangerous and they want you to slow down on that road. They'll time the lights so that you keep hitting red lights as you drive. As long as you're driving within the reasonable speed limit, you should be hitting red lights. And those are all mathematical equations, formulas that are programmed into that traffic system. I could go on and on. Your GPS devices on your phone also use mathematical formulas to locate where you are and to find your position uh, in the world, in the country, in a city, in a specific neighborhood. Mathematical trigonometry formulas are used to do that, and so that's all programmed by a human being. Okay, so this language is used all around us, and there's thousands and thousands of more examples that I'm not going to get into, but hopefully you get the idea. Okay, and my job here in this unit is to introduce to you some of the rules that go into this language. Okay, so we're going to start with just baby steps and just start with our building blocks. A lot like when you're learning a new language, let's say the English language, right? If you were to see the letter M, right, the letter M doesn't mean much to you. But then as you realize that when M is mixed in with other letters, they can form words, and it forms sounds when it's beside other letters. So there's rules to how that language works, right? And then even words don't mean that much until you see it in a sentence. So you see a collection of words in a sentence. And even sentences don't mean all that much until you see a collection of them in a story or a novel, for example. So just like you learn the English language, we are now going to take kind of the baby steps in learning the mathematical language of algebra. Okay, so let's begin. Let's scroll down here to the start of our lesson, and it is what's called the Introduction to Polynomials. Okay, polynomials meaning basically poly is kind of the Latin word for many, and nomials, think of it as variables, okay, or terms. So we're looking at the introduction to many different terms, for example. So almost like combining letters like in the English language. Okay? So let's take a look at just the building blocks here. I'm going to start very straightforward. So we're going to simplify expressions by doing something called collecting like terms. So this is collecting like terms is one of the rules in algebra. Okay, one of the rules that you have to follow if you're communicating mathematically. Okay, so for example, how could you simplify the following picture? All right, so we see here that there are 3 cats, right? Then 1 mouse. Then 3 more cats and 3 mice. Okay, now obviously when you're looking at that, wouldn't it make sense to, instead of saying that there's 3 cats, 1 mouse, 3 cats, 3 mice, wouldn't it make sense to add together the cats? So if there are 3 cats here and 3 cats here, wouldn't it make sense to say that there are in total 6 cats plus there are 1 mouse plus 3 mice plus 4 mice. So I took this expression. Let's think of this up here. Let's think of this as an expression of 3 cats plus 1 mouse plus 3 cats plus 3 mice. And I did what's called simplified it. I said, okay, I'm going to take that expression and I'm going to add the terms that are the same. Essentially, I'm going to add the pictures that are like each other. And that is 6 cats plus 4 mice. So that's what this lesson is all about today. It is about simplifying or collecting, in this case, pictures, but in our case, when we do it mathematically, it's going to be called like terms. So instead of like pictures, they're going to be like terms. Okay, and we're going to look at what that means. So that's essentially what we'll be doing, and obviously it's going to get more involved as we go. But let's continue to explore this idea of collecting like terms. And this is a great question that I love to do when I'm teaching this. Okay, is it a coincidence that 2 times 3 plus 5 times 3 minus 4 times 3 is equal to or is the same as 3 times 3? Okay, is that a coincidence? Well, let's see what this equals here first. I mean, let's work this out. 2 times 3 is 6. 5 plus 5 times 3 is 15. And then minus 4 times 3 is 12. Let's see what that equals, okay? So we've got 21. 6 plus 15 is 21. Minus 12 is 9. And let's take a look at now my other side. 3 times 3 is what? Also 9. Is that a coincidence? The fact that all of these numbers here are being multiplied by 3, and then this number here, this number 3, is also being multiplied by 3. Is that a coincidence that these are both equal to 9? Did I just, happen to pick these two, let's call them expressions, okay, and say that they both equal 9? Well, why do they equal each other? Let's explore this. Let's imagine this almost as if the pictures of the cats and mice that we saw earlier. Okay, so instead of saying cats and mice here, what I'm saying in this expression is basically saying let's say there are 2 mice plus 5 mice minus 4 mice. So instead of the number 3, I'm using what I showed it earlier in the picture, these mice here, okay, to represent the number 3. So how many total mice would I have? I'd have 2 mice plus 5 mice is 7 mice. Minus 4 mice, I would have 3 mice. Okay? Just like here, I would also have 3 mice. If I let 3 be represented by the word mice, I would also have 3 mice there. So what did I do? Why are they equal? What I did was, because all of these were 3s, I was able to do what's called collect like terms. They are all like terms because they are all being multiplied by the same number, the number 3. So what I do is I add what's called their coefficients. So the 2 is a coefficient because it's in front of the 3. The 5 is what's called a coefficient. It's in front of the 3. And the 4 is also a coefficient, which is in front of the 3. So because they were all being multiplied by 3, I was able to add and subtract their coefficients to simplify it down. So I was able to do 2 plus 5 minus 4 to get 3. Okay? And that is essentially continuing on, giving you more knowledge of what we'll be doing today. Okay? Is we are going to be thinking of, we can always relate back to when we see, for example, these 3s, we can always relate back to, okay, what if it was the word cats instead of the 3s? Because we know that if we said 2 cats plus 5 cats minus 4 cats, we would know that that, of course, is 3 cats, right? But suddenly you throw a number in there, like 2 times 3 plus 5 times 3 minus 4 times 3, and suddenly that might not be so obvious to us. So if you constantly think back and you constantly relate it back to words to describe those numbers, you may find it easier. Okay, let's keep going. And this is just going to become more and more clear to you as we go. So if you feel confused right now, don't worry. It will become more and more clear to you as we go. Okay, so let's keep building on this knowledge here and keep trying to understand this. What if we replace the 3 with an x? Are they still the same expression? Well, remember our linear equations, right? The linear equation I showed above. There were x's and letters involved in those equations. Remember the one that I just wrote above? Okay, well, what if now, instead of the number 3, we used x in our equation? So we have an x instead of the 3 there, and there, and then also here. It is the exact same thing as what we did above. Because they are all x's, we can add their coefficients. It's just like, again, saying 2 cats plus 5 cats minus 4 cats. They all have the letter x. They're all represented by the same number because they are all represented by the same letter. So all we need to do there, to do 2x plus 5x minus 4x, because they're all the same letter, we can just add and subtract what's called their coefficients and simplify it. So we can just simply get 2x plus 5x minus 4x. Well, if I just do 2 plus 5 minus 4, I again get 3. But instead of the word cats or mice, or instead of being multiplied by 3, I now have the letter x. So I have 3 x's. I have 3 x's left over when I do 2x plus 5x minus 4x. Okay, so yes, they are equal, right? If this is 3x here, this can be simplified to also equal 3x. But I can't stress enough, these letters have to be the same for you to add and subtract these coefficients together. For example, you can't do you can't say 2 cats plus 5 mice is 7 cat mice. You can't say that. Okay? All you can really do is simplify to the point where it just says 2 cats plus 5 mice. That's as low as it can go. You can't simplify that any further because they're different. They're different objects. They're different variables. You can't add them together. It's the same thing in math. If you see x's, if you see terms that have x's, then those are like terms and you can add and subtract them together. If, for example, this was an x, but this over here was a y, would we be able to add 2x plus 5y together? No. You would just have to keep it as 2x plus 5y, a lot like 2 cats plus 5 mice. Okay? So certainly there are some similarities here with what I'm talking about. So hopefully you're starting to get the idea of what like terms are. Like terms have to have the same variable or the same letter. And when we do, we can add or subtract their coefficients. Okay? Let's keep going. Last part, which I kind of touched on already, is 2x plus 5x minus 4y equal to 3x? No. And I described it above. Because this has a y as the variable, you cannot subtract that with the 2x plus 5x. All this would be simplified to is, well, 2x and 5x, they both have the same letters. So it's like saying 2 cats plus 5 cats. Well, that would be 7 cats or 7x. But then you have minus 4 mice, for example. Well, you can't subtract cats and mice. You just have to leave it the way it is. So you would say 7 cats minus 4 mice, or 7x minus 4y. So is it equal to 3x? No, it's certainly not, because we cannot combine these because they have different letters. Okay, we can't do 7 minus 4 there because they have different letters. Let's keep going now just with some terminology, and then we'll get into some examples. And actually, I'll do the examples in another video. This will just be my entire introduction video. So now let's look at some new words relating to polynomials. So 4x squared, 5x, 3a, negative 7y to the power of 3. These are all examples of terms. Okay? They're all examples of what's called terms. I've already described to you what the coefficient means. So we need to learn this terminology, just like, again, if you were learning a language, you need to know what vowels are and what consonants are, and you need to know what syllables are, and all of these things. You need to learn that to properly learn a language. Well, we need to learn this terminology to also learn our language. So if you see a number with a letter, that's called a term. If you see a number with a letter, that's a term, that's a term, that's a term. Even if you just see a letter, it's also a term. Okay? If you just see a number, it's also a term. So let's look at the types of terms now. You can have what's called a monomial. A monomial means you have one term. One term. So an example is 2x, let's say. That's one term together. Even though there's two things there, together, because they're being multiplied together, like 2 times x, that is one term. What's a binomial then? Well, that is two terms. So a binomial might look like this: 2x plus 5. Okay? So that is, let's say, a binomial. It has two separate terms separated by an addition or subtraction sign. Okay, so it's separated by a addition or subtraction sign. So if you hear me say binomial, that means that an expression has two terms in it. Two terms, each of them separated by either a plus or minus sign. A trinomial, 3 terms. Okay, so it could look something like this: 2x squared, let's say, minus 8y plus 10. That is a trinomial. It has 3 terms. Here's one term. Here's my next term, minus 8y, and then 10 is my next term. And notice that they're all separated again by a plus or minus sign. Okay, so there's a minus sign there and there's a plus sign there. Okay, so we have what's called a monomial, that is a single term, a binomial, that is 2 terms, and a trinomial, which has 3 terms. Okay, so again, this is just terminology we need to know, just like when you're learning a new language. Okay, you'll need to know things, like I said, like what's a vowel, what's a consonant, what's a syllable, and so on and so on. Okay. All right, now that's where we get to our definition of a polynomial. Okay, it is poly meaning multiple. It is the sum of one or more terms. So it could be anything. It could be a 1-term expression, a 2-term expression, a 3-term expression, all of that. Okay, now I should explain to you what is the difference between an expression and an equation. So expression versus equation. Well, an equation, everybody, has to have an equal sign. Think of it as like a formula. It has to have an equal sign. So in our last unit, we did linear equations, and they all had equal signs. Like, for example, C equals 75x plus 500, right? That had an equal sign. An expression is just like that, only an expression does not have an equal sign. So all of these here, this, and this, notice there's no equal sign. Those are called expressions, and they're different from equations. Expressions aren't really, they're almost like the building blocks towards an equation. So an equation could be made up of expressions, for example, but it's not an equation unless it actually has an equal sign. So think of an expression as being just almost like the building blocks of an equation. So they are different. So if you hear me say an expression, I am saying, I'm referring to something that does not have an equal sign. It's not a formula. It's not an equation. It's simply mathematical language. Okay? Whereas an equation actually has an equal sign, okay? And you can think of formulas, for example, that have equal signs. That is what an equation would be. Okay? Now, before we get into some real examples, let's just identify like terms, okay? Which we've already done above, but let's identify what like terms are. Out of these four, which are like terms? Basically what I'm saying is which one has the same variable or letter, but also the same exponent. So this, and this, they all have the letter x. That makes them like terms. Okay? The 4y is not a like term with the others. So if we saw 2x, 3x, and negative 9x in an expression, we would be able to collect them together. Basically say 2x plus 3x is 5x, minus 9x would be negative 4x, for example. 5x minus 9x is negative 4x if you did that on your calculator. Okay? But we wouldn't be able to do anything with that 4y. That 4y has to just stay the way it is. Well, what if now we had 3x squared, 4x squared, 4m, and 3x? Which ones of those are like terms? This one and this one. I know what you're thinking. You're probably thinking, but sir, there's also, this has an x variable as well. How come that is not part of the like terms? It's because one of the mathematical rules, okay, just like when you're learning the English language, there are rules to sounds coming together, silent sounds and whatnot. One of the mathematical rules is that like terms have to have the same variable and exponent. So see how these have exponents of 2 and they're the same? That is what makes them like terms. So not only do they have to have the same letter, they have to have the same exponent. Okay? That's something that you just have to remember. And I can go into describing why that is right now, but that might go into a little bit more depth than I want to get for this lesson. Okay? But just know that to be a like term, they have to have the same letter and the same exponent. Just like up here, what is the exponent for 2x? If you don't see an exponent there, that really means that the exponent is 1. So it's like that all of these x's have an exponent of 1. That means they're all the same. That means they are like terms because they all have an exponent of 1. In this case, I have my x's, 2 of them have an exponent of 2. They're like terms. This is not a like term. This is not a like term. They have to have the same exponent. Okay? That concludes the introduction part to this lesson. And what we went over was just a quick introduction on what algebra was, which was a language, a mathematical language. And we are learning our first set of rules to learn this mathematical language, and that is what's known as collecting like terms. Okay? That concludes this video. In the next video, I will go through all of these examples where we are going to simplify these expressions by collecting like